Welcome to today's video. Today we're going to introduce the notion of linear independence. Basically, the idea is that for a linear combination, some vectors in that linear combination might be redundant, meaning we could get the same values, the same span of a set of vectors by using less, by deleting some of the vectors from the set. And this is made more precise by the notion of linear independence. So let's start with the definition. Little warning up front. This definition will be a little formal, but I will show you in examples in later videos how to actually use that definition. And hopefully it will become clearer why this is a suitable way of defining linear dependence and linear independence. So, as usual, we'll start with a vector space. So let V be a vector space. As usual, just think of R to the n. Let R be a number, and V1 to VR be a set of vectors in V. Then that set of vectors, V1 to VR, is called linearly dependent So we'll first define what linearly dependent means, not linearly independent. That will be the next step. So this is called linearly dependent if there is a linear combination of these vectors that produces the zero vector, but with at least one coefficient not being zero. So let's write that down. That set is called linearly dependent if there are scalars lambda 1 to lambda r in reals with at least one of those not equal to 0, such that the linear combination induced by these scalars, so the sum lambda I vi, I from 1 to r, is the zero vector. Now please note, of course, if all those scalars are chosen to be 0, the real number 0, then the result of this linear combination will be the zero vector. So that is always possible. The question that linear dependence asks is that possible in some other way? So apart from this trivial way to combine the zero vector as a linear combination of that set V1 to VR, is there a different way of doing it? If that is the case, then our vectors will be called linearly dependent. And now we know that. Linear independence is the opposite. Meaning if that's not possible, if there is no non-trivial combination of the zero vector, then that set of vectors will be called linearly independent. Otherwise, the set V1 to VR is called linearly independent. And let's write down that idea in other words as well. So what that means is the vectors, or the set of vectors, is linearly independent if the only way to get the zero vector as a linear combination of that set here is to set all coefficients to 0. In other words, V1 to VR is linearly independent if the zero vector can only be obtained as a linear combination of V1 to VR by setting all coefficients to 0. So the sum of lambda I vi I from 1 to r is the zero vector, implies that all the lambdas are the real number 0. And as I said, please note the zero vector is always contained in the span of any set of vectors. You just have to set the coefficients to 0. You can always produce a zero vector. So linear independence means that there is no other way to obtain the zero vector. Whereas linear dependence means there is a non-trivial way. So this setting all coefficients to 0 is called a trivial linear combination of the zero vector. So let's write this down. The vector 0 can, of course, always be obtained as a linear combination of any set of vectors by simply setting all coefficients to 0. Linear independence means there is no other non-trivial linear combination that would yield 0. So what exactly does that mean in terms of redundancy of vectors? Well, what it means is if vectors are linearly dependent, then there is at least one lambda in that chain that is not 0. So if the set of vectors v1 to vr is linearly dependent, then there is a solution lambda 1 to lambda r in R of that equation lambda I vi equals the 0 vector where at least one of the lambda 1 to lambda r is not 0. And that means we can solve for the corresponding vector. And that means, in turn, that corresponding vector is indeed a linear combination of the others. So linear dependence means at least one of the vectors can be expressed as a linear combination of the others. The important thing to note is that this need not be the case for all vectors. There is one that is a linear combination of the others, but that is not necessarily true for all of the vectors. Okay, so in this way, linear independence means the set of vectors that we have is redundant, or is irredundant, sorry, in the sense that no vector can be expressed as a linear combination of the others. So linear independence means the set of vectors is irredundant in the sense that no vector can be expressed as a linear combination of the others. And thus, removing a vector from a set would change its span. For the linear dependent case, removing a vector from the set might also change its span. So be careful about that. Linear dependence means there is a vector in that set that we can remove without changing the span, but it's not necessarily true for all vectors. Linear independence means, regardless of which vector is removed, the span is always going to change. So let's have a quick look at what this means for our theory of systems of linear equations. So let's say we have a system of linear equations in echelon form. What do we know about this? For a system of linear equations, let's say A, B, in echelon form. Now let's consider all the rows that have pivot elements. Then these rows form a set of linearly independent vectors. Because if you want to obtain the 0 vector, then we will have to multiply each of those rows with 0. Otherwise, there is always this one entry, the pivot entry, that we cannot remove. So we know that all rows that contain a pivot element form a set of linearly independent vectors. And of course, the same is true for the columns that contain a pivot element. Thus, what we can say is, well, the number of pivot elements of the matrix A is equal to the rank, by definition of the rank. So the rank tells us how many linearly independent rows and how many linearly independent columns there are in this left-hand side A. So the rank of A is the maximum number of linearly independent rows of A, and at the same time the rank of A is the maximum number of linearly independent columns of A. Now we'll use this notion of linear independence basically to define an irredundant system that generates a given vector space in one of the upcoming videos when we talk about the notion of a basis of a vector space. I'll see you then.